Let's work some numerical examples based on what we've just been looking at. And this first one, actually a fairly simple problem. Find the fraction of nitrogen molecules, N2 molecules, in the n equal to 0 and the n equal to 1 vibrational states at 300 Kelvin. And for this, you need to know what the vibrational temperature is. I looked it up online for nitrogen. N2 was 3374, was at least one of the values that I found. And this is an application of that the fraction or the probability. The fraction of the molecules in the nth state is the number of particles in the nth state divided by the total number of particles. So it's the probability of finding the system in this vibrational state M. And from the previous segment, we'd gotten this formula here. And we just need to calculate that for m equal to 0 and m equal to 1. So for the ground state, m is 0. Theta vibrational we're given, temperature we're given, so it's really just plug in and crank through the numerical values. And you see the probability of this vibrator being in the ground state is probably so close to 1 that we would say it was all the particles were in that state. We can't get the number, the probability that they're in the state m equal to 1. That's the first excited state. And that's just the number of particles in that state divided by n if you've got a system. And again, it's the same formula above up here. The only difference is now m is 1. Plugging m equal to 1. So there's our 1. We've actually got both the temperature and the vibrational temperature, and the vibrational temperature. And when I calculated that, I got this factor here times essentially 1. In fact, it doesn't, on my calculator, didn't give anything any different. But that's the probability that it's in the first excited state. So virtually all the, at 300 Kelvin for nitrogen, all of the atoms in the gas are going to be in the ground state. There'll be just a very almost insignificant fraction of the particles that will be even in the first excited state, and the higher states are even less probable. So kind of an interesting result. It says that generally you're okay with just looking at the ground state.